Okay guys, so welcome back again to our next video, which is about the nitrosyl ligands, right? Okay, when it comes to nitrosyl ligands, you need to know a few things, right? There are two modes of bonding towards our metal center with our nitrosyl ligands. The one is the bent mode and the other thing is the linear mode, right? So you know what's the meaning of this thing, right? So if we take the metal center like this, and the bent mode means we have nitrogen and oxygen. There is a bent. When it comes to linear mode, which means they are linear, like this. But the thing is, you need to know a few points which are very much important when it comes to the questions. First thing is, let's talk about the bent mode, right? When the ligand is connected to our metal center, you know the ligand contributes by donating some electrons, right? But when it comes to the bent mode, you need to understand there will be one electron, only one electron will be donated to our metal center, right? But when it comes to linear mode, the donated electrons will be three electrons will be donated. This thing is very important when you like calculating the number of electrons of a complex, right? It is much important. The complex accept the 18 electron rules. This is much important. We will talk about some examples later in this video. For now, you need to understand, if your nitrosyl is connected to a metal center through bent mode, then there will be one electron is donated by your nitrosyl ligand. If it's linear, then 3 electrons would have donated to our metal center. Okay, the next thing is you need to remember that when we are finding the oxidation state of the metal center, let me take an example for it. Okay, let me take another call. Okay, for finding the oxidation state, right, you remember a thing like this. Let's take a simple complex like this, 3 nitrosyls. Okay, now if I ask you what is the oxidation state of this metal center, what are you going to do? You're going to remove each of these ligands and check whether what is the amount of charge left behind by each ligand, right? Like an example, there is a carbonyl. Carbonyl removes as a neutral compound, right? So there will be no charge left behind. When it comes to nitrosyl, right? When it comes to nitrosyl, there are two modes of bending, modes of connected. So each mode will act independently based on this oxidation charge contribution. When we talk about the bend, right? When you talk about the bend, you need to know the nitrosyls leaves by giving positive charge on metal center, right? So this nitrosyl ligand, if we remove it, then it will leave a positive charge on our metal center. You need to remove that. The opposite will happen on linear. It will give a negative charge on metal center. This is very important. So if I go to the example, if I ask you what is the oxidation state of this metal center if the nitrosyls are bent, then what would be your answer? So you know carbonyls leaves as neutral compounds, so no charges will be left behind. But nitrosyls, they leave a charge. When this bent nitrosyl is leaving, it will put a positive charge on your metal center. Here, positive charge on your metal center. So what happens is, there are 3 nitrosyls which are removing, each giving a positive charge to our metal center. So total will be positive 3. So the oxidation state will be positive 3. What if your nitrosyls are linear? Now it's not bent, it's linear. Now you know carbonyls are removing as neutral compounds, so no charges will be left behind. But nitrosyls, they are linear, they leave by giving a negative charge on your metal center. So total of 3 nitrosyls will be removed by giving at each negative charge to a metal center with the oxidation state is -3. That's how you find, right? That's how this bent mode and linear mode applies to our complexes. I hope you get the idea. Okay, now the other important thing is, what if I ask a question like this? Okay, let me remove this first of all. Okay, now the question is this, right? You know carbonyls, right? We are very much familiar with carbonyls and the backbonding effect. So what can you tell about the nitrosyls backbonding effect of phi acceptance? You need to remember that nitrosyls are better phi acceptances than carbonyls. These are better backbonding effects. These are giving better backbonding effects. These are not giving a better backbonding effects compared to nitrosyls, right? This comparison is based on backbonding effect. Or phi acceptance. You know what the phi acceptance means, right? Phi acceptance means what is the tendency to this nitrogen atom to accept electrons from the metal center, right? So when it comes to that factor, nitrosyl is the dominant, not the carbonyls. Why is that? So to look at why is that, we would need a molecular orbital diagram. Okay, let's draw a molecular orbital diagram like this. Okay, here we have it. So one, okay, now here we have 3. Okay. So this is, you know, p orbital of carbon, and this is the s orbital. This is the p orbital of oxygen, and this is the s orbital, right? Now what is the difference between the carbonyls and nitrosyls? This atom, right? This is here we have a carbon, here we have nitrogen. Okay, now the thing is, okay, I just made a small mistake. There should be another sigma here, right? Now it's okay, right? Here we have bonding and antibody here. I hope you know the molecular orbital diagram, right? That's why I didn't say anything when I draw it. Like if you have not have a good idea about molecular orbital diagram, I'll put the video on this screen. You need to look at it before you come into this particular explanation. Okay, now what's the difference between the carbonyls and nitrosyls? The carbon and nitrogen atoms. If I ask you a question like this, what is the most stable atom, right, based on the p orbitals, right? Based on the p orbitals, what has the most stable p orbitals, whether it's carbon or nitrogen? It's nitrogen, right? Why? Because nitrogen has lower radius, but carbon has, compared to nitrogen, it has higher radius. It's based on the proton values, right? Atomic number. So nitrogen has lower radius than the carbon, which make it stable when it comes to the p orbitals. Okay, now if I draw the p orbitals of nitrogen, look at this. I will draw it using a yellow color. This is the p orbitals of nitrogen. Here we have the s orbital of nitrogen. Oxygen doesn't change, right? For both cases, oxygen is the same. So the energy of the p orbitals of oxygen doesn't change. But because of these atomic orbitals changes its energy, right? These molecular orbitals, they will also change, right? They will, you know that when it comes to nitrogen, it has reduced its energy. So the molecular orbitals are also reducing its energy, like this. The yellow color is represented by nitrosyls, right? Okay. So this is what we are important. This is the 5 star of nitrosyl, and this is the nitrosyl 5 star of carbonyl. Okay, now if you remember about backbonding, we have talked about it. When the backbonding happens, our metal center is there. It will donate its electron density towards this 5 star orbital, 5 star antibonding orbital, right? So now I am going to ask you a question. Which is much efficient to our metal center, whether to donate its electron density to our carbonyl's 5 star orbital or nitrosyl's 5 star orbital, right? If your electrons donated to this state, right, is it stable compared to this one? No, right? If your electrons can donate to this particular molecular orbital, it is much stable than this one because it has low energy. That's why nitrosyls are better for acceptances than carbonyls, because they are stable, right? They are stable when it comes to backbonding. So you need to have that idea, right, when you are explaining the answer. So I hope you got the idea about this nitrosyls and backbonding effects. So now let's move into a simple exercise, right? Okay, let me give you the exercise. Okay, so this is the question, right? So I'm going to ask you the question about the geometry or the bending, the connecting mode, right? The bonding mode of nitrosyl ligand. So the question is, in this case, in this complex, does this nitrosyl act as bending mode or linear? In this case, does it act as bending mode or linear, right? That's the problem. So the hint is, both these complexes, right, both these complexes accept the 18 electron rule. Now take your time and try to find out the what causes to this bending or linear mode. So then I will do the question. Okay, now the hint says it accepts the 18 electron rule. So I'm going to find this complex's number of electron without taking the nitrosyls, right? Without taking the nitrosyl. So they are accepting the 18 electron rule. So which means the total number of electron should be equals to 18, right? So what I'm going to do is, I'm going to forget the nitrosyl is there and take all the electrons of the others, and I'm going to see what's the difference between the 18 and the amount of electrons what I get. Let's do it. So you know the cobalt, right? The cobalt is having S2D7 electron configuration, which means the total number of electrons as 9. There are arsenics giving 2 electrons. There are total number of 4, which means 8. And we have plus 2, right? We have plus 2, which means we need to remove 2 from our total electrons. Let's see the total. We will having our total as 15. But we have been told that the complex accepts the 18 electron rule, right? So this electron value, the amount of electrons should be equals to 18. So how many are missing? 3 are missing, right? So with this 3, we can take it as 18. So what we didn't take is the nitrosyls. So there should be 3 electrons which is contributed by the nitrosyl. In order to donate 3 electrons, the nitrosyls should be at linear mode. Same like this, right? So I know cobalt is totally giving 9 electrons. Arsenic, there are 4 arsenics, so it means 8. There is a plus positive charge here, so I'm going to subtract 1. And there are NCS, which is giving another 1 electron. So the total value is 17, right? Total value is 17. 1 is missing in order to take the 18 value. So this nitrosyl over here, it should donate 1 electron to our complex in order to perform the 18 electron rule. So this should be in bent mode. because the bent mood provided 1 electron here. In this case here, bent mood providing 1 electron, linear mood providing 3 electrons. That's how you talk about this question. And also you can take the oxidation value too, right? You know that if this is linear, a particular oxidation value can be achieved. In this pair, a particular oxidation value is achieved. So you can do this question based on the oxidation value too. So I hope you get some idea about the nitrosyl ligands. We will talk about more on these topics in next videos.